Okay, it's my great honor to introduce our speaker today. Dr. Kinfe Teweldebirhan is an assistant professor at Aksum University. He got his PhD of astrophysics from Addis Ababa University in 2018 with Mark Mish as his advisor. After that, he worked at Aksum University Physics Department, teaching and mentoring graduate students. Currently, he is a scientific visitor at NCAR HAO. Kinfe has been working on the solar dynamo. He studies the nonlinear impact of converging flow into active regions or bipolar magnetic regions on the global solar magnetic activity of the sun in the framework of a three-dimensional Babcock-Leighton solar dynamo model. He is also currently working with Sarah Gibson at HAO in studying coronal magnetic field evolution using the simulated photospheric magnetic field of the sun from his dynamo models. Let's thank our speaker again, and Kinfe, you can start your seminar.
Okay, thank you, Rizu, and thank you for giving me this chance to present my work on the COFFIES members. I'm Kinfe from Aksum University, so I should start the presentation. The title of my presentation is the magnetic field dependent inflow towards active region and their nonlinear impact on a 3D Babcock-Leighton solar dynamo model. So, okay. Next. It's not working. Okay, good. So presentation, here are the presentation outlines: introduction, solar magnetic activity and its impact on the Earth. This is actually a very brief introduction for the COFFIES Seminar members. So, and the stable dynamo development, like the flex emergence as a spot maker algorithm, as a source term, and modeling the bipolar magnetic active regions, the inflow, its observation, implication, and mathematical formulation of the inflow field. Then we'll see the simulation results from evolution of two BMR inflows. They are consequence on the meridional circulation, and they are consequence on the polar field build up. Then we'll see the simulation of solar activity cycles, comparing the two type of solar dynamo quenching, and as a plan or future work, we'll see a very brief on the coronal magnetic field and solar cycle. As you all know, the sun is an active star whose magnetism has a direct impact on the Earth and our technological society. As you can see here, the large eruption towards the Earth, and it's good to understanding this magnetic activity and magnetic cycles of the sun is crucial. So then I will see the flex emergence. What is the flex emergence? And this is also a very brief. The magnetic field lying in the solar interior emerges to the solar surface, as you can see here, on the photosphere of the sun, as a simple or simplest form of the bipolar magnetic active regions. In this talk, we are going to use the BMR and sunspot or active region interchangeably for this presentation. This is the full disk of the magnetogram that shows the line of sight of the magnetic flux density on the photosphere of the sun. As we can see here, the sunspot, the site of strong magnetic field on the photosphere, and they appear as a dark site in a white light observation. And this is the leading and trailing spots with opposing magnetic field, that is the halopolarity, and the leading is slightly closer to the equator, to the heliographic equator, and this is the Joyce law, and this polarity is reversed with solar cycle and hemisphere, actually. The solar activity is associated with the sunspots, as you can see here. This is the number of spots versus time. The number of spots decrease and increase with solar cycle. This number of spots approximately, the number of such spots are actually approximately in the period of 11 years, and we call it the solar activity cycle. And these are the sunspots are a manifestation of solar magnetic cycles, best manifestation of solar magnetic cycles. And briefly here, this is the butterfly diagram. The sunspots emerge at a mean latitude, and through time they move towards the equator. That resembles in both hemispheres. This resembles the butterfly wing, and we call it the butterfly diagram. And this shows that the latitude versus time of the sunspot regions of the last 22 years. And now I will talk about the Babcock-Leighton dynamo. The sunspot cycle is linked to the internal dynamo. And as you can see here, the line of magnetic field in the convection zone shared by the differential rotation and form the toroidal magnetic field. And when the toroidal magnetic field becomes strong inside the convection zone, they become buoyant at the surface and get twisted due to the Coriolis force here, and emerges as a bipolar spots at the surface tilt angle. And to complete the cycle, actually, this magnetic flux move transported to the poles and submerged there with opposite magnetic field lines, like the first one in the figure in the upper panel. This is now what is stable does. The stable is developed on the success of the Babcock-Leighton dynamo model, which is the two in a plane of radius and latitude, and the module of flux, the surface flux transport magnetic field generated in the 2D, the latitude and the longitude. So stable is a surface flux transport and Babcock-Leighton dynamo model, which is fully 3D hybrid of this Babcock-Leighton dynamo model and surface transport model, which is the stable solves the kinematic MHD induction equation. As you can see here, this is a 3D rotating spherical shell, and we use a source term as a the BMR emergence at the surface, which is called we call it the spot maker algorithm, and the velocity consists of, which is inferred from observation, consists of the meridional circulation, differential rotation, and BMR inflow will be discussed soon. So, and Itati is the turbulent diffusivity here. These are the model ingredients. This is the differential rotation, which is fast at the equator and slow at the pole. This is the meridional circulation, which is the blue shows the counterclockwise, and the red is clockwise direction, which is the stream of mass flux. And this is the turbulent diffusivity that we use in our model, actually. Okay, the sunspot maker algorithm, which is the source term for the polydial field, is that is explicitly emergence of sunspots and dispersal of this BMR at the solar surface, and gives the polydial field, and which is actually connect, which is in responsible to the spot producing toroidal field, toroidal flux near the base of the convection zone. Actually, this is integrated over a tiny layer at the base of the convection zone. So when this be hot greater than the threshold value, which is set threshold value at the base of the convection zone, we place a spot at the surface, the BMR at the surface, which is in response to the Joyce law and Hall polarity actually with the hemisphere. Okay, and we determine the content of the flux in the BMR based on the observed data and determined by the long normal distribution at the surface. After that, we extrapolate it downward actually to some penetration radius 0.9. This shows the beneath of the BMR looking up actually. So this is the time delay between the sunspot emergence actually, which is determined by the probability density. We don't want to place spots every time step. So in addition to the threshold value at the base of the convection zone, it is also limited by the time delay, the time delay between the two spots. This shows the P tau and PS shows that the mean and mode of distribution for the probability density function based on observation data. Okay. And now the stable produces the magnetic cycles, as you can see, the 22 magnetic cycles and the 11-year of solar cycle, and it produces this nice movie, as you can see, the emergence of sunspots at the surface, and they get shared by differential rotation and the meridional circulation transport this flux towards the pole and the development of polar field. This is the mean polodial field that shows the reverse of the polodial field. Next, what I will present is the converging flow. What is the motivation? Here again, we will use BMR inflow and converging flow into the active region interchangeably for this talk. So in addition to the bulk motion, the differential rotation and meridional circulation, active region establishes a large internal circulation. So these are observed. So variety of helioseismic observations have detected and analyzed these specially extended converging flows with an average of 10 to 30 amplitude of the inflow, the magnitude of the inflow, and they can be extended up to 30 degrees away from the center of the active region. Okay, if this is so, this is actually the converging flow are believed to be induced due to the cooling. As we have said, the active region is cooler than the corresponding the surrounding active region relatively. So this is the converging flow is induced by enhanced radiative cooling in the active region. As we can see here, this is the side view of the large scale internal circulation. We can see here, this is the inflow on both sides, and the outflow at certain depths. These are the outflow due to the conservation of mass. Actually, this outflow is the flow connected to the observed inflow, maybe connected to the observed inflow at the surface. So what is the implication for the dynamo? The converging flow, this converging plasma flow towards active region squeezes the opposite polarity, the magnetic field together. And there could be a flux cancellation. That means the trailing flux, it prevents the trailing flux from moving to the pole and the leading flux from moving to the equator. So this process leads, this flux cancellation leads decrease the amount of magnetic flux in the active region. This also could have an influence on the structure and evolution of active region by itself, and for the development of polar field at the surface, as well as for the development of polar field build up. In general, it can influence the solar dynamo operation, the global solar dynamo operation. Let's see the mathematical formulation of the inflow. Spatial and temporal variation of the inflow is directly proportional to the magnetic field distribution at the surface. This equation is adapted from Cameron and Sushler 2012. This is the surface magnetic field, surface flow at the surface, so which is proportional to the smoothed magnetic field at the surface. Horizontal gradient C is to control the speed of the inflow. This is at the surface, and horizontal gradient when it is at the surface. And taking the absolute value of the magnetic field at the surface and smoothing it, that enhances the flux cancellation actually, and will take the absolute value at the surface. So this shows that the stable produces this placement of bipolar magnetic regions at the surface. This shows that magnetic field at the surface, when we take the absolute value of this magnetic field, we got this, it becomes unipolar because we take the absolute value, and C shows that the inflow toward the active region. So the inflow is towards the active region actually. In this, as you can see here, it is not to the individual. The inflow is not to the individual polarity. It is towards the both the polarities. So the resulting inflow velocity is proportional to the gradient of smoothed magnetic field, smoothed absolute magnetic field at the surface. So the converging, the components of converging flow. Once we take this equation at the surface, and the mass flux at the surface is completely polydial components, then after some mathematical simplification, we can have the three components of the flow: the inflow component, the radial component, the latitudinal component, as well as longitudinal component. So let's see the illustration of these components in this form. This is the radial component actually. Black shows that inflow into the active region, or that means downward flow, and this periphery, the white, shows that the outflow at different choice of radius. This is at the surface, and this is some deeper down, 0.96 of radius or solar radii, and some deeper down again that shows the black downward flow and white outward flow. This is the latitudinal component of the inflow or the flow. This shows that this is at the surface, still the white shows outflow and black or blue shows that the inflow at the surface. And as you can see here in the right panel of this, it reverses the flow deeper down. So it reverses the flow as we have already shows this, that the inflow at the surface is outflow deeper down, and that shows our model shows that we can illustrate it in the latitudinal and longitudinal flow. The flow at the surface reverses down flow at some radius, as you can see here, in 0.96. Our penetration radius goes all the way 0.9 solar radius. So this shows that the reverse of the flow. Okay. We did a parameter study, and we start with 1 and 2 BMR in each hemisphere, and this shows that 2 BMR placement in each hemisphere, and when they get distort and dispersal by the differential rotation and meridional circulation, after some time, 3 years, we can see the polar build up, the polar migration towards the equator, and these sunspots are emerged at 25 degrees in each hemisphere. So, we will see what the contribution of the inflow in this 2 BMR. So, in this, that shows that this is the meridional flow. The meridional flow at the surface. The blue curve shows that the usual meridional flow, and the variation around the blue curve is the contribution from the inflow. We use 10 meters per second inflow. That is the contribution from the inflow. This is from 2 BMR inflow, 1 in each hemisphere, placed in each hemisphere. And as you can see here, the BMR inflow alters the meridional circulation. This is the right panel shows that the BMR inflow in each hemisphere, or many BMR inflows in each hemisphere, and the black shows that the usual meridional flow at the surface, and the gray is the variation around this black due to the introduction of the inflow, the components of the inflow, that shows the component of the inflow on a latitudinal or around the meridional flow at the surface. What looks like here, this shows that the development of BMR, the development of polar field with different choice of inflow velocity. So when we take large amplitude or large speed, we can notice that the polar field reduced much. So this is the factor we identify how the efficiency, how it can affect the polar build-up, this the inflow amplitude, and in the right, that shows that it has also a contribution from the smoothing area. For when we take a smoothing area, it can also influence. Then the red, this without smooth, and the others, when we take large smoothing area, we can also see that the contribution for the polydial or polar field build-up is also reduced. Okay. When we take many BMRs for our model, we know that the kinematic induction equation with kinematic induction equation, this admits a growing or exponentially growing or exponentially decaying. But we need some non-linearity to stop this growth, this exponential growth, to determine the amplitude of the magnetic cycles. So the question is, what limits the dynamo growth? And to produce a stable solution for the kinematic induction equation that produce the dynamo growth. The magnetic field dependent inflow is one possibility in a nonlinear feedback that can stop the growth of the dynamo. And the other question we can ask is, does this is sufficient to stop the dynamo growth is the other question. Yes, and we'll see. Actually, traditionally, we have been using to stop to quench the dynamo growth, we include some term in the polydial field or in the source term in this form, but now we can include to stop the growth. One possibility is the magnetic field dependent BMR inflow. We do have also another non-linearity to stop the dynamo growth, that is the tilt angle saturation dynamo quenching. That is when the magnetic flux emerges to the surface, it can twist due to the Coriolis force actually. So, and this tilt is due to the Coriolis force. If the magnetic field that emerges to the surface is strong, it doesn't have much time to twist this flux. So it depends on the magnetic field that emerges. It depends the strength of the magnetic field that emerges to the surface. The tilt angle depends on the strength of the magnetic field. This is also another nonlinear feedback that stops the growth of the exponential growth of the magnetic field. And this is the that shows the magnetic cycles that reproduce from the tilt angle dynamo quenching simulation with Karak and Mesh 2017 in order to facilitate comparison with the magnetic field dependent BMR inflow quenching. This is the mean radial magnetic field at the surface, and it is corresponding polar build-up above latitude of 70 degrees is this. So figure shows that the toroidal magnetic field at the base of the convection zone, and its corresponding magnetic field. The toroidal magnetic field is given by this over the entire hemisphere. So let's compare this with the magnetic field dependent BMR inflow as a quenching. Here we use 10 meters per second, and we turn it off the tilt angle quenching term, and we use as a quenching term the inflow only in this model. So that is only 10 meters per second, but clearly we can see that the amplitude of the polar field is decreased. And we can see also from the color table in this, the sunspot emergence, they become weak and they become fuzzy. And weaker polar field, lower amplitude cycles, we can clearly compare from the tilt angle saturation dynamo and from the from the inflow saturation dynamo. They reduced much the polar field, the amplitude of the polar field build up. So that means there is enhanced flux cancellation. So let's compare this two models. In the tilt angle, this magnetic cycle is actually in 140 years of time, as we can see from our previous. It is from 460 up to 600. So this is in 140 years of time. The average cycle period is 10.5 years. Its corresponding average cycle period for the inflows dynamo saturation is 12.5 years. And the number of reversals for the tilt angle dynamo is 14. The number of reversals for the corresponding tilt angle saturation dynamo is 11, around 11. So this shows that we know that the polar field development is a budget for the subsequent toroidal field, and the toroidal the period is connected with the toroidal field at the base of the convection zone. So when the polar field becomes weak, the toroidal field also becomes weak. So the toroidal field at the base of the convection zone is weak. So the time for the reversal, the time for the average cycle period increases due to the weak toroidal field. When the toroidal field at the base of the convection zone becomes strong, we can expect more emergence of sunspots at the surface. So, but this is weak. The BMR emergence delayed and makes the polydial field production slower. So it depends on the toroidal field at the base of the convection zone. Actually, the time that the time delay for creation of sunspots at the solar surface. So that is the reason that makes it slower or long polarity reversals and the average period of the cycle. We have said that the inflow, the parameter inflow is 10 meters per second. Its speed is 10 meters per second, but it depends on the magnetic field actually in the cycles. This shows that the maximum velocity of the inflow, but it's around 20 meters per second, that shows. So it depends on the magnetic field on the solar cycles. The inflow depends on the magnetic cycles, actually. Okay. Saying this, let's also compare these two dynamo saturation type. This is the number of hemispheric, this is the sunspots that emerge on the surface, and these are smoothed sunspot numbers for the magnetic cycles. We have already shown some 3 or 2 slides back, and its corresponding sunspot number for the tilt angle dynamo saturation shows in figure left panel, this figure. But for the inflow dynamo saturation get very weak. So the number of sunspots, they become smaller in the number of sunspots. That means we can say that enhanced number of spots at the surface due to the inflow, due to the BMR inflow. The other striking result we have seen in our model is if we use large inflow amplitude or strong BMR inflow amplitude, total shutdown of the magnetic cycles, it kills the dynamo operation, total dynamo shutdown. That means that the observation that shows the amplitude average. It can go actually up to 50 meters. Some reports shows that the amplitude is up to 50 meters per second, but the average is 10 to 30 meters per second. This inferred from the seismic observations are more than enough for the substantial impact on the dynamo of operation on the framework of stable or Babcock-Leighton solar dynamo. And indeed, it can also saturate the dynamo. Next one, I will look at a brief, or I will present a brief on the future work is the coronal magnetic field and the solar cycles. So the solar magnetic field we observe on the photosphere of the sun and spreads all the way to the corona, and the heliospheric is linked to the internal dynamo. And this solar coronal evolution is linked to the variety of solar cycles, and indicating that the coronal evolution is governed by the solar dynamo, or by the solar interior, mainly the convection zone. And again, the sun's surface magnetic field, especially the polar field, we have been presenting the polar field, which is measure of the polarizal field, can be set as a boundary condition for the coronal heliosphere magnetic field. So this produces by the stable that shows that the solar surface magnetic field, radial magnetic field at the surface, and that can be used as a boundary condition for the corona. And we can determine or we can study the evolution of coronal magnetic field at the in the corona. And what we can do here is that the potential field source surface magnetic model as the PFSS can be used the boundary condition of the stable, the magnetic field at the surface, and we can determine the magnetic field at the corona. This shows that the magnetic field at the corona, and we can determine which one is open and which one is closed magnetic field from the simulated magnetic field of stable, which is the solar surface magnetic field, which is radial magnetic field at the surface. And this shows that after we extrapolate the stable solar surface magnetic field to the PFSS to the PFF extrapolation, and we can identify these coronal holes by the forward modeling. That is in order to compare with the SDO EUV simulation, and that shows that this is the plane of the solar disk, and this is the Carrington longitude, and for the SDO AIA 160 angstrom. Yep. Saying this, we can also determine the lifetime and the position of the coronal holes at in the corona. So we will study we will run a parameter study to determine the coronal holes at the poles as well as at low latitude, and we can also, it's possible also to create a butterfly diagram of coronal holes like this. This is from UNIS to 2023. We can determine with different parameter studies like the tilt angle versus inflow conching. And we can also use the variation along the tilt angle variation to determine the lifetime and the position of the coronal holes in the corona. This shows actually the good study of this is the lifetime of the latitudinal coronal holes extend up to 3 years. The recent study shows in 2023 by Hunes. Okay, now the conclusion, the converging flow, this BMR inflow are observed phenomena on these are observed phenomena, and we cannot ignore them in our study, the Babcock-Leighton solar dynamo, because when we include more observational studies, it can enrich the model. So these magnetic fields affect the operation of the global solar cycle in the framework of the stable, and we observe that, or it shows that flex cancellation within the BMR inflow itself, and this also decreases the polarial field as well as the polar field development, and it can determine the amplitude of the subsequent cycles. And it's also on their own field, it can determine the amplitude and the period of the cycle. So we cannot ignore them simply, these important ingredients for the study of the solar cycle. And as a starting point, we can use this the stable reproduces the important figures or the basic figures on the solar cycle observation, and we can use as a boundary condition to study the solar corona or the coronal evolution on solar cycle on solar cycle actually. Thank you very much. You can find the recent, I have submitted the paper in archive in this link. Thank you very much for attending. If you have any question, I'm happy to see your comments and to answer questions. Yeah. Thank you.
Oh. Okay. Thank you. We already have a few questions in the chat. So we start from the question in the chat. Sushant, do you want to ask?
Yeah, very impressive work, Kinfe. I have so many questions, but let me start with asking, do you have nonlinear Lorentz feedback included in the simulations? If yes, how do the inflows affect differential rotation?
Okay. Thank you. Yeah. The answer is yes, it is nonlinear because I would like to so it is nonlinear. So as you can see in this equation, it is three-dimensional. It has a contribution on the longitude as well. So it can affect, it has a contribution to the differential rotation, but we did not actually see how much it can affect the differential rotation, but it can affect. So as you can see here, this is the contribution for the longitudinal longitudinal component of the inflow.
Right, but this figure seems to suggest that the east-west inflow would cancel out, having no net effect on differential rotation. Is that right?
So this is the contribution to the east-west, and the flow is summation of the meridional circle, the overall flow in the model in the induction equation is summation of the differential rotation, meridional circulation, and the inflow, it contributes on the meridional flow plus on the differential rotation, but I cannot tell how much it affects the differential rotation, but it has a contribution. So it's good to, it's a good question.
Okay, you can ask me.
Can I comment there? Yeah,
Sure.
all right. Yes, so it does not have Lorentz force feedbacks. So it is not yet. We can add it. It's based on the Ash code, or Bidyakarek is working on a version that's based on the Raleigh code. So it's easy to link in Lorentz forces, but as a first approximation, we were going to make it kinematic. And I think you're right that these would cancel out, that the net effect on the longitudinally average differential rotation would cancel out in these.
Yeah, it has contribution.
Can I ask a question related to this?
Thank you. Yeah.
Well, so my question is related to this. So even without the Lorentz force, conservation of angular momentum, and I think one of the papers you cite on this topic implies if you have an inflow at the surface, there should be a corresponding vertical motion induced. And I can see you haven't included it yet, but for future work, it might actually be interesting to include the effective set as well.
I think, yeah, actually, I didn't have time to send, well, I had some issues, so I didn't send for comment my paper to you, but yeah, we can include that as well.
Yeah. So we didn't include it, but it's something, if you're talking about an inflow, conservation of angular momentum independently of the Lorentz force, tells you probably should have a vertical flow. And this, of course, will be interesting as well.
Okay. Thank you very much. But yes, yeah, we can include it, and we can see, even we can determine how is the contribution of the longitudinal component on the differential rotation. We can also implicitly see its contribution on the retrograde of the longitude.
Yeah, nice.
Yeah.
Okay. One more hand raised by Junwei. Junwei, do you have a question?
Oh yeah, sure. So I'm wondering whether the inflow outflow reversal depth matters in your simulation, because I saw your inflow and outflow reversal depth happened around 0.96 solar radii. I think this is a bit deeper than most of helioseismic observations. Not sure if this matters, just wondering.
Yeah, actually, the reversal is at 0.92, deeper down, no reversal until 0.96. But yeah, it could be, it depends which radius we are taking. So in our case, we take the penetration radius 0.9. So somewhere deeper down, it should be it should show the reversal. So it is, yeah, it could be deeper than the heliosismic observation, but this is in our model, we take that observation, but I'm not sure about the heliosismic observation at what point shows the reversal. But even some other, okay, shows that the reversal could be even lower. So this shows that the side view of, and it is deeper, but we didn't take that much deeper.
But that's something that's easy to change, and would be interesting to look at what effect changing that has.
Yeah, we can set the model whatever we like. It depends the penetration, the radius we take. It depends the reversal we take. It depends on the boundary conditions we are concerning.
Good, thank you.
Okay, any other questions?
I have a question. Could the Coriolis force acting on the inflows, does that change the tilt of the active regions?
Well, yeah, the Coriolis force acts on the tilt. So as I have said, the tilt gets depends on the strength of the magnetic flux that emerged from the convection zone. So if it is strong, it doesn't have much time to get tilted. If it is weak, and it becomes more tilt, and we can also consider the torque on the strength of the magnetic field actually. So yeah, it is the Coriolis force that makes it tilt.
Oh, my question is after the active region has emerged and you have inflows going into the active region, Coriolis force that acts on the inflows, could that change the tilt of the active regions?
Okay. At this time, the reason that makes it inflow is the we know that it is from the reduction of, or the gradient reduction of the induced from the cooling, but it depends on the magnetic field. This inflow is,
but the question, I think the question is slightly different, and the question goes back to the comment I made a little bit ago. The observations show, so not only do you have an inflow, but it becomes twisted in the same way a hurricane would. And this is conservation of angular momentum. And this is also the Coriolis force acting on the inflows. And you haven't studied it, I haven't studied it, but it would be an interesting thing for you to study in the future. Yes.
okay, yeah, I see.
Yeah, Kinfe, if you want to go to the next slide, I think it's the next slide, or it's next one after that. Where the equations are. Oh, maybe it was before that. Anyway, yeah, so we use the poloidal. Yeah, that one. Yeah, so it's purely poloidal, so it doesn't have any vertical vorticity, doesn't have any twist. But yeah, I agree with Robert. This is something that we could easily add in and see what difference it makes. See,
yeah, I think that would be interesting. Yeah,
maybe more some. It could be we can have more nonlinearity if we consider that again. Yeah.
Okay. So Mark, your hand is still raised. Is that for just the comment just now, or you still have a question?
No, that was just the.
Oh, okay. Okay. Any more questions? Okay. Let's thank our speaker today. Again, it's a very nice talk and very good discussions afterwards. So the recording of the talk will be put online, same as before, and we will see you next month at our next seminar.
Thank you very much.
Thank you.
Thank you, Kinfe.
Bye.
Thank you.
Thank you.
Thank you, David Cameron. Thank you all.